Hi BBK49. It is time for what I believe will be the second to last video before we're done with this course. In the last video, I showed you how you can collect the data, and then afterwards, in the video afterwards, I showed you how you can label the data as lying, running, walking, and standing. And today we'll actually use this data to train an algorithm that can then detect just from the accelerations collected which movement a person is doing. Let me start by sharing a screen here. Let's first go over the things that I'm using here in my working directory. So first, obviously, I have the lab for functions. Then I still have the acceleration data, txt. That's the one that that's my data from collecting the classification experiment. So when we do the walking, running, sitting, and standing, that obviously doesn't have to be here anymore, but it's still here for me. And then in the labeled data folder, before there was the labeled data CSV file from my labeling the data in the last video. And now I put in all the files that we need for the classification and for the lab or the tutorial today. So as I told you before, we can download once everyone has uploaded their data. We will either send you a folder, or you can or we'll tell you where to download all the data from your colleagues, and then you have to save each individual labeled data file from your colleagues and yourself in the labeled data folder called labeled data 1, labeled data 2, labeled data 3, and so on. Whereas the first ones will be the ones from your own group members and yourself. So let's say you have like 4 group members, then you'll have label data 1, 2, 3, and 4 will be your group members, and 5 to 55 or whatever will be all the other colleagues. The reason for this is because we will use your colleagues' data to train our algorithm, and then we will check if it actually works well and check the performance and the accuracy of the algorithm with your group's data. So in the very end of this tutorial today, we'll actually feed the algorithm with the data of your own group, and then we'll see if the algorithm can detect if someone was standing, lying, running, or walking. In my case, because I don't have that much data yet at the time of the tutorial, I have 5 data sets, whereas actually I think 1 or 2 of them are duplicates, and then some of them are from other people. And label data 1 is my own data set. So I will train the whole algorithm with data sets 2 to 5, and I'll check afterwards how good the performance was with my label data 1 file. So here I have my code prepared. I've called it lab for main code. I have some, let's maybe reset everything here. Reset, and then yes, so that our variable explorer here is empty. So I have some various libraries that we need today. I'm not going to go into detail with this, but those are all the libraries that you will need at least for what we're going to do now. Then I have prepared for you guys a function in the lab for functions library that imports all the data. For this function, you need the label data folder, and in this folder, you need all the files calls 1, 2, 3, 4, 5, and so on. So if you run this, what you'll actually get, it will load all the labeled data files here, and then you'll have one big file that tells you the x acceleration, the y acceleration, the z acceleration, the time, the activity, and also the ID, so like which subject was it. So if I go down, at some point it will change to ID 2 and so on. So it's really the whole data set of all the subjects that we have. Okay, that probably takes too long. Oh, there we go, ID 2 now. So it's all the data in one file called data. Then what I did next is I decided which data I'm going to use to train the algorithm and which data I'm going to use to test the algorithm. So here I really just have to say so my data train is basically the data of the ID field that is bigger than 1, because in my case I want everything from 2 to, in my case I think 5, to be, or everything that's bigger than 1 has to be in the training set. Okay, so I say that everything where the ID is bigger than 1 should be in the training set. Okay, and then that's the same as the same here is everything that is smaller or equal to 1, which in my case is just 1, will be in the test set. So if you, for example, have 4 subjects in your, or 4 people in your group, and 1, 2, 3, 4 will be your group, and the rest will be the rest of your colleagues, then everything that is bigger than 4 should be in the training set, and everything that is smaller or equal to 4 should be in the test set. And what I did here then was, and I'll show you that maybe here if I go to training set, because the index here starts at, what's that, 28,860. We want this to start at 0 basically. So, I mean, that's not super important, but I just like it because it might make it easier in the future. To make this start with 0, from 0, not from 28 something, I just use a code here called reset index. So you have to say data train equals data train dot reset index. And then I say drop equals true, because usually with the reset index function, it creates a new column with the new index. But we don't want this. We just really want the actual index being the new index. So if I now say data train equals this here, and now we have a look here, then the index here starts from 0. And I do the same here for data test. In some codes, this is important because you need the index afterwards. In this, I'm not 100% sure. I don't think I'm actually going to use it, but it's still important to know for other things. Okay, and then here, let's just have a, because we want to have like a little bit of an overview about what's going on with the data, especially when you guys have like all the data from all your colleagues. You want to see what's the distribution of the data. For me, that's not going to be that exciting because it's just 5 subjects, but I'm going to do a count plot which shows us the distribution of the activity here. And if I run this, then you can see that we have that many data points of standing, that many data points of lying, of walking, and of running. And here we can, for example, see that standing, that we have the most of the data points are actually standing. If one of the activities is incredibly disbalanced, so like, let's say, for example, if standing would be now many more data points as lying, like let's say, for example, 10 to the power of 100 or so, then you'd have to think about changing something in the preparation of the code. So maybe just deleting a few of the standing data points, or simulating more of the lying and walking, that you have like actually more data of lying, walking, and running, and so on. In our case, we don't have to change anything, but I just want you guys to know that this is usually something that you have to think about in machine learning and activity recognition and so on, that the activities are kind of like balanced in about the same way. And then with this part of the code, you can see how the distribution between subjects is. So, oh, why is that not working? There we go. So here you can see how many data points per subject are in there. So again, that's really just for you to have kind of like an idea what's going on. And if there was one subject, for example, that had like 3-4 times the amount of data points, you might have to think about what was going on there. Maybe go back to the data and see if there's some kind of like mistake or something like this. So those two, so before you actually start with anything with a machine learning algorithm or so on, you want to understand your data set. And these are good ways of like visualizing the data set, that you can see if everything looks kind of like, okay, that's how it should be. And you might find some mistakes or problems in the data by plotting a few different things. Okay, and once we have plotted everything, or like those kind of things that I just told you, then we can go into preparing our data set specifically for the machine learning algorithm. For this, I have prepared for you guys a a function. This function basically really just looks at the data set and uses the nature of the data set and then prepares it for our machine learning algorithm. But before this, there are two things that are really important. So we have to tell the algorithm. So what we're doing here now is we're creating windows. So now we have like for each subject, we have one long data set, which tells us that this data point is running, this is walking, standing, and so on, right? And what we want to do there now is like we want to create windows. So we want to create a window of a few seconds, and we say that this window, like there's some kind of like X, Y, Z data, this window was standing. This window was standing, this window was standing. And so not just for each data point, but we want to know for each window, what did this person do in there? And now we have to decide how long do we want these windows to be? And then also how much should this window shift? So first of all, we are going for a window length of 100, which in our case will be 4 seconds because we are collecting data with 25 Hertz, meaning that 100 data points is 4 seconds. And then if we would say for the step 100 here, that would mean that we take this data set here or this part of the data set. This is one window, and then we jump the whole window, and then this will be the next window. What we actually want to do today is we say 20 here, which means we have one window here, and the next window will just move by a fifth of the window, and this will be the next window, meaning that 80 data points here will be in the first window and in the next window as well. And that's just because that's called a moving window. So it's just like moving forward. And you know, in this window was walking, and so on. And at some point it might be standing or whatever. And then this function here basically uses the time steps and the steps, and then it creates those windows that we need afterwards for training the algorithm. So we do this for the training data. So it creates it for the training data here. Oh, I need to define that first. The training data here. Okay, and then the same for the test data. So how does our data look like right now? Let's have a look at the test ones, okay? So if I open the X test here, what you'll actually get now is a 3-dimensional data set, meaning that you have X, Y, Z in the first dimension, which is like, or so 1, 2, 3 axes, or yeah, 3 columns in the first dimension, which is the X, Y, and Z acceleration. And then you have 100 data points for this one window. And then if you go in the third dimension is then the window. So if I say now 2 here, oh, there we go, work. 2 here, then it jumps into the second window. 3 would be the third window, but it's closed on me now. So 3, what's going on here? Voila. Oh, there we go. So those are the different windows that we can jump into. So it's like 3-dimensional. We can't see it anymore. That's why we have to jump between the windows. That's the same for the training data. And then the Y data is basically like, so the first window was standing, the second window was standing, the third window was standing, and so on. So if we go back to X test here, we know that this here was standing, this here was standing too, this here was standing too, and so on. So these ones here, the Y belongs to each window, and that's why we have 1,438 values here, because we have 1,438 windows here, and we want to know for each window which class, which activity did we do. And then lastly, for the classification algorithm that we're going to use, we need to encode our Y variable. So for now, we have like standing, with standing, walking, running, and lying. But what we want to have is an encoded one. So like the algorithm needs a binary number here, basically. So I'm going to show you what will happen here if you use this part of the code here. And if we now go to Y test, we actually have not just the standing, but we have 4 axis here, and that's a binary number. It's in 0, 0, 1. So if the third column here is a 1, then we know that it's or the system knows that it's what was it before? Standing, right? And if you go down here, then this will probably be running. And then if you go down here, standing again, running, standing, walking, standing, and so on, right? That's just how the function that we'll use afterwards for the algorithm that we're training. It's just that the way how it needs it, okay? And the one hot encoder, I love the name, is a function that we're using from this library here that automatically does what we want it to do here. And at this point, we're already creating the architecture for the neural network that we're going to train afterwards. So I didn't talk about this yet, but for our machine learning algorithm, we're going to use a deep neural network. Specifically, we're going to use what's called a recurrent neural network with a long short-term memory. This is way too much for this course right now, but if you want to look into these kind of things, then yeah, look for deep neural network tutorials on YouTube, look for recurrent neural networks tutorials on YouTube, and look for long short-term memory recurrent neural networks on YouTube, and you'll find some cool explanations. Especially I like the 3 blue, 1 brown tutorials on YouTube. So those are very, very good and very understandable. So I'll just put the link to this YouTube video here. And if you want, you can just check it out, which is a very general explanation of how deep neural networks work. So that's why I actually created a the architecture, or a function that creates the architecture, because that would just be yeah, too much for this course. But if you want to look into what we exactly use, you can just go onto the lab for functions, and then you can look here. We used 128 units and so on. And the long short-term memory basically means that it also that the algorithm, while it's looking at the data, it's also remembering what has happened before. And this is supposed to be for accelerometer data and for activity data and so on, a very good algorithm. So let's create the architecture model here. And then here we're already starting to train the model now. So when we train the model, it creates a big architecture with a lot of what's called units. It's working like it's basically an artificial brain. And when we train the data, or yeah, when we use the training data, what the computer does, it basically creates a lot of different parameters, which in the end lead to the right solution. And now we can train this model with our training data set. So what we do, what training the data means is that the model will get fed with all the data from our training data set. In my case, that's subject 2 to 5. In your case, that will be all your colleagues that are not in your own group. It will have a look at this data, and it will learn and understand from the acceleration, or hopefully understand from the accelerations, which movement the subject did at this moment. So when training the data, it will not just get the acceleration, but it will also get the actual activity for each. So it will get the windows with the acceleration and the activity for each window, so that it can somehow learn an algorithm that connects the activity with the acceleration. And then afterwards can hopefully, just by getting the acceleration, detect which activity that was. So that's why here we will use the training data and also the Y-train, so like the window activities. And then we also have to specify how many epochs it has to do. An epoch is when it uses all the data and it learns. And then usually you just don't just do this once. It also depends on the size of your data set. But in our case, or at least for this tutorial now, we will use 20 epochs. So it will go over all the data 20 times and try to optimize for the right parameters and for the perfect algorithm to afterwards detect the activities just with the acceleration. So this also means the bigger the data set is and the bigger the epochs are, the longer the algorithm will work. That's why for us, we'll use 20, because I believe that with the data set that we'll have in the end, that it will still take like a while. Like it's not just going to be click and that's it. This will be an optimization task that will take, can be a half an hour, can be an hour, might even be 2 hours. But I think the 20 epoch should probably work. It's not going to take days for the different computers that we'll have in this lab. And then also what I also did is I said that I want to have a validation split of 0.1. So that's 0.1 in that case means 10%. And what it does is for each epoch, it takes 10% of the data, puts it aside, trains it with the 90% of the with the other 90% of the data, and then in the end it always takes the 10% that it didn't use for training, and it basically tests the performance. So for those 10%, it takes those 10%, gets the acceleration and decides by itself what it thinks which activities those were, and then it checks it with the actual activities, and then you'll with every epoch you'll see how high the validation accuracy actually was. So if I run this now, it will take a while, so I'll probably stop. So we're back now. The algorithm is done calculating, and here you can see for each epoch what actually happened. So at the very last one here, we can see that it has an accuracy of 98%, actually 99%, but this is for the 90% that it used in this specific epoch for training. And it has an accuracy, a validation accuracy of 94% when it actually calculated the accuracy for the 10% of the data set that it did not use for the training in this specific epoch. Actually, you can see here how the accuracy is constantly going up. Obviously, sometimes it falls down again, but it's going up because the algorithm is learning with each epoch, as well as the validation accuracy is also going up. But to see that a little bit better, we can plot here the training accuracy and the validation accuracy, and both of them are constantly except of this, whatever that was. It's constantly going up, which is what we want. But what we actually want to know now is how good is the accuracy if it of our algorithm now, or sorry, the accuracy now of this specific model. How good is the accuracy of this specific model now if we don't tell it anything about the activity? So it really just gets the acceleration. It has to detect by itself now what's the acceleration, what's the activity. And for this, we can use this line here. So this function here basically takes the accelerations of our test set. So in my case, of this one subject that was not in the training set at all. And for each window, it takes the accelerations and guesses which activity that is. And then it checks if that's the actual activity. That's why we also give it the y-test, and will let us know the accuracy in the end. And if we go on accuracy here, we want to know the second variable here, and here we have 0.99. So that is basically 99 or almost 100% accuracy. Before we go on with this, I want to show you guys how you can also calculate the accuracy by yourself, by hand, basically. To do this, we just calculate our web predictions. So in this line here, I'm actually doing two things at the same time. First of all, just predicting for the accelerations for each window, I'm basically predicting which activity it is. And then I'm also back transforming it already. So back transforming means that my result won't be a binary 0, 0, 1, 0, but it will already tell me if it's standing, walking, or whatever. So if I run this here, then my Y predictions now will be the predictions of what I did in each, or what the subject did in each window. And I want to compare this to the actual y-test. So the Y prediction is the prediction, and the y-test is what the subject actually did, how we labeled it. And because from before we still have the binary one here, we also want to back transform this here so that this one is also in normal actual activities again. So now we want to see for each window, so the y-test and the y-predict are now the same length because, yeah, they have to be because the same data set, right? And now we want to compare if for each y-predict, is it the same as for each y-test? So the y-predict, the first one, for example, we predict our code predict standing, whereas the y-test is actually standing as well. So that would be right, for example. So what we're doing now here is I'm just looking if y-predict equals y-test. So if it's the same, it will give us a true. If it's not the same, it will give us a false. So I just call it is same. And then I calculate, so if we go on is same here, where is that? There we go. Go here. So here we have true, 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 and so on and so on. We have a lot of truths because we have 99% accuracy. And then here we have 3 false, for example. Those 3 were predicted the wrong way. And now I want to calculate the sum of these. I want to know how many truths do we actually have. And the sum here is 1,433. So 1,433 out of 1,438, because that's the length of this whole array, are actually right. So now to calculate the accuracy, we really just have to calculate the length of the array. So all possible activities, or so yeah. So we have to do we have to divide them. So we calculate the percentage of all. So how? So now we need to calculate of all possible activities. So of all 1,438 activities, how many have been right? So that's how we calculated the sum before. And now we say is same sum divided by the length, which will give us a ratio 0 point something. And this is our accuracy then. And if we calculate this here, and then we go here to accuracy, then this is the same as we had with this one function, 0.996. So if you calculate this by 100, that's the percentage of accuracy that you're having. So we have 99.65% accuracy, which is actually pretty good. But that might just be because I duplicated some of my data sets so that I have enough data sets for this tutorial here. And lastly, we can visualize our results. So again, we want to have a look at our data. We want to actually see what's going on to understand it a little bit better. So what we're gonna do here is a confusion matrix. A confusion matrix shows us what were the actual activities and what were the predicted activities. And you can see which activity was predicted better, which one worse, and so on. So for this, I've written a function called plot_cm, cm for confusion matrix, and this needs as an input y-test, which is already back transformed here, so we don't need to back transform it here anymore. Okay, so it needs as an input y-test, then the y, so like this is the actual activities, then the predicted activities, and then it needs to know the categories, all the categories that were actually in this whole experiment. And this is in this variable here that we created before already. And if you go on categories here, there we go. So if I click on this and then on this here, those were all the activities that we had in this experiment. So we had lying, running, standing, and walking. So if we run this here, then we can see here on the y-axis, we have the actual activities. So we have walking, standing, running, and lying. So here we know we had 319 windows of lying. So 4-second windows of lying. Then 286 windows of running and so on. Or actually, sorry, that was a mistake. We actually had 319 plus 1 for 320 of flying, 289 of running, and then 3 plus 510, 513, 514 of standing, and so on. And then we can see that these are the predicted ones on the x-axis. So 319 of the lyings were actually predicted as lying. But then also 3 of the standing ones were predicted as lying. Then for running, it's actually pretty good. So 289 were predicted right, but 1 was actually predicted. So one line was predicted as running, and so on. So here you can get a feeling of what's going on in our data here. That's almost it with the course. I'll do another video for the step counting afterwards. But with this, we're done with the classification. Obviously, what's important for me to say here as well is that this is a general algorithm. So if you, for example, want to use this algorithm now to train something else, like for example, stair walking, walking up, walking down, doing side steps, or whatever things, you can use data from a lot of people, feed it into the algorithm, train the algorithm, and then test the accuracy again with some extra data. So you can use this algorithm for whatever you want. I'm sorry if I didn't go more into detail today. I believe that this would be too much for this course, but there are a lot of incredibly good YouTube tutorials which explain how deep neural networks and recurrent networks and so on work way better than I could ever do. So please go ahead and check out YouTube, search by yourself. You'll find something cool, but as I said, I'll put one general deep neural network tutorial in the explanation. If you'd like to watch it, it's pretty cool and it's pretty cool explained. I really like it. With that, I think I'm done for today, and I'll upload the rest or the next video hopefully pretty soon. See you guys. Bye-bye.